All right, here we are. This is video number 3 from section 3.2, and we are on page 12 of your notes there in the second part of example 5. I don't know why I stopped that previous video before we got to part B, but anyway, this will be a good little review of what we were talking about in the last video. So in part B, it's asking us how long before the culture contains 20,000 bacteria. Remember back in part A here, we had come up with our value for K. Let's see, right down here to be about 0.47. So therefore, we can use that right here in our formula. Our initial amount is 500 bacteria. We've got e to the negative 0.4 or to the positive 0.47 times t for time. So on this next problem here, we are going to have, again, the formula is A of t equals the initial amount, which was 500 bacteria, times e to the 0.47 t. Now, ideally, we wouldn't use just 0.47. We would use the big unrounded version from our calculator. You may not still have that in there, though, since this might not be the same day that you did part A, so that's understandable. They're wanting to know, when is the culture going to contain 20,000? So you're going to put 20,000 in for the amount after time t. Divide both sides by 500. $20,000 divided by 500 is 40. Take the natural log of both sides. The natural log of e to the 0.47t is just 0.47t, because the natural log of e is 1. So really all you have to do now is take the natural log of 40 and divide it by 0.47, and that's going to give you your t value. So natural log of 40 divided by, and I do have that previous answer stored in there. When I divided, I got about 7.8 hours. Okay, so that is 5B. Now, let's move on to number 6, which is using a regression model. So for this, you're definitely going to need your calculator. We've got a chemist starting out with a 100-gram sample of a radioactive substance. This table is showing the amount of radioactive material at the end of the week for a 6-week period. We are trying to fit an exponential function to the data. So switch over to your calculator, and we need to put this data into our stat. Edit. In list 1, we're going to put the weeks. And in list 2, we're going to put the weights. And those are in grams. All right, so remember then what we do is if we want to see the data, I'm going to go to my y equals and make sure that's all cleared out, which it is. I'm going to go to second y equals, turn on stat plot number 1. Make sure that the scatter plot is chosen here. The lists in which you put the data are chosen here. The type of mark you want to use is here, and then if you have a color calculator, it'll ask you for the color. Then quit out of that and go to Stat Calc, and it asks for an exponential function. And so that's down here, choice 0, exponential regression. Hit enter. If you have an older calculator, you will not see this screen. Your calculator will just have expreg on the home screen, and then you just type in where you want it to store the regression equation. And on those old calculators, you have to go to vars, yvars, function, y1 in order to get that. On the newer calculators, you can just go to alpha trace, and there's the list of the y values there, and you can just choose y1 from there. Oops, I just cleared mine out. I gotta redo it. Set calc 0. Okay, now I'm going to calculate. So here's my regression equation. A is 102.3061 times a base of 0.869 to the x power. So that's the equation that I'm going to write down over here on the other page. So I have copied that equation right over here to our notebook. And so the equation that we are looking for then is going to be y equals A, which is 102.3061, times B, which is 0.869-ish to the x power. So that's our exponential function. Part B asks for what is the half-life of that radioactive material. That means how long before half of it is gone. So in the original problem, they told us that we started with 100, 100 grams. So half that much would be 50 grams. And then we just solve this, divide both sides by 102.3061. So if I take 50 divided by that, I get 0.4887 equals 0.869 to the x. Take the natural log of both sides. Remember, you can pull that x out in the front. That's the whole purpose of taking the natural log. So you can get the x out of the exponent. And then divide both sides by the natural log of 0.869. And we get about 5.1 for x, so we'll round it to about 5 weeks there. Our times were given in weeks originally. Next question there is, what is the next question? When will there be 10 grams left? So there you just put in 10 on the left-hand side. Let's see, it was 102.3061. I guess I should do that. 3061 times, was it here, 0.869 to the x. Divide both sides by that 102.3069 again. That's 0.0977 equals 0.869 to the x. And take the log of both sides. Divide both sides by the natural log of 0.869. And you get X to be 16.6 or around 17 weeks there. And last question, how much radioactive material will be left after 52 weeks? So there you're looking for what is A at X equals 52. So this one's easier because you just take the 102.3061 times the 0.869, and you know that that is raised to the 52nd power. That is your X value there. And so just type this directly into your calculator. Turns out to be, I think it was about 0.1 grams. Let me see, 102 point. Yeah, it's about 0.1 grams. And so that would be what you would have left there. We're going to stop this video right here. This is video 3. There'll be one more short video with the rest of this section. See you later.